Hey guys, I just wanted to do kind of a continuation from the lecture on Thursday night on November 5th. So today I just wanted to talk about a couple of examples of like diagonalization. Well, I also want to show that every square matrix has a complex eigenvalue. Okay, so our first example, um, this is a kind of an example that's continued from Thursday, but let's let A be this upper triangular matrix 1, 3, 0, -1. We're going to find a invertible matrix P and a diagonal matrix D such that A equals PDP inverse. And if you recall, we already did some computations, and that turns out that's enough to give this factorization. So let's recall like what we found out about A. We found two eigenvalues, 1 and -1, and corresponding to 1 we have the eigenvector 1, 0. Well, there's many choices, but this is just one example of an eigenvector corresponding to 1. And we have the eigenvector corresponding to -1. We have 3, -2 is our choice. All right. Now you can see that V1 and V2 are linearly independent, so they give a basis for R2, and so we have a basis of R2 consisting of eigenvectors for A. So you just put them in a matrix. So you see we put V1 in the first column and V2 in the second column, and therefore we put the eigenvalue, we put the eigenvalues in the same order. So if lambda1 is the eigenvalue of V1, we put lambda1 first and then lambda2. Okay? And if you work it out, you can calculate PDP inverse and you get back A. Right? Yeah, okay. Right. So let's do another example. Here I have a matrix Q, and this is an orthogonal matrix. Okay, so what we're going to do is try and find a diagonal matrix D and a unitary matrix U such that Q equals UD U star. And what do we do first? Well, we just try and find the eigenvalues. The eigenvalues are, so we have to find the characteristic polynomial. We do Z times the identity. The identity matrix is 1, 0, 0, 1. We multiply it by Z. We subtract A. And then we take the determinant, and that gives us a quadratic polynomial. Okay. So we get, Z minus A is this matrix. Z minus 1 over root 2, 1 over root 2, -1 over root 2, Z minus 1 over root 2. We compute the determinant. We get this times this minus this times this polynomial, Z squared minus root 2Z plus 1. Solving that equals 0 gives us two eigenvalues, root 2 plus or minus root -2 divided by 2. Or we could rewrite it as root 2 times 1 plus or minus I divided by 2. Okay. Those are our two eigenvalues. We're going to rewrite the entries. Remember, Q is 1 over root 2, 1 over root 2, -1 over root 2, 1 over root 2, and we're going to write 1 over root 2 as 2 over root 2. Or sorry, not 2 over root 2. We're going to write 1 over root 2 as root 2 over 2. Right? Same thing. Just multiply top and bottom by root 2. Okay, so now we're going to try and look at Q minus our first eigenvalue times the identity and try and row reduce. So when we do that, our first entry is going to be root 2 over 2 minus this number, which so that will give us So we get root 2 over 2 minus root 2 over 2 minus root 2 over 2i. So we're left with negative root 2i over 2. Here we have negative root 2 over 2, just rewriting this. We have root 2 over 2, and then we have the same as down here is negative root 2i over 2. And now if we do, you know, row 3, replace row 3 with row 3 minus I row 1, or sorry, row 2 goes to row 2 minus I times row 1, we get zeros. Okay. Now, I want to find a vector in the null space of this matrix. Well, I'll just do, I guess, what would work? Root 2 over 2 minus I root 2 over 2. So yeah. Okay, so this is gonna be so let me explain better what we should do. Well, I'm sorry if that has been there for too long. Okay, so all we do is we take our first choice of eigenvalue, we do q minus the eigenvalue times I, and we row reduce, and we end up with this. Well, the null space is spanned. A basis for the null space of this matrix is just what will work, 1 minus I. Okay, and now we want a, when we want to have a unitary matrix, we need to find an orthonormal basis consisting of eigenvectors, so it means we need to divide by the norm of this vector. So the norm of this vector is the square root of 1 squared plus 1 squared is root 2. Okay, so this up here. So that means we're going to take u1 to be this vector divided by root 2. Okay, so and then remember this has eigenvalue I guess it was eigenvalue root 2, 1 plus I divided by 2. So let's remind ourselves what that means. It means q times u1 is root 2, 1 plus I over 2 times u1. But one thing we know about q is that it's q has real entries. So we conjugate both sides, we get q conjugate u1 conjugate equals this number conjugate, which is just root 2, 1 minus I over 2, u1 conjugate. Okay, but q has real entries, so the conjugate of each entry of q is just the same as it was before. Oh my, I've done that again, sorry. Okay. I was just writing down what does it mean for u1 to be an eigenvector of q? It just means this. I mean, just take that equation, take the complex conjugate of both sides, and now we just use the fact that the complex conjugate of the entries of q are just the same as the entries of q. So that tells us that the conjugate of u1 is an eigenvalue, or sorry, is an eigenvector for the conjugate of this eigenvalue. Okay, and what's the conjugate of u1? We'll call that u2. That's just going to be 1 over root 2 I over root 2. Okay. Right, again, I have to practice not doing that, sorry. Okay, but anyways, here's u2. So, sometimes that's nice. You kind of get an eigenvalue and an eigenvector for free. Okay. So now what happens, so now we want U to be our unitary matrix. We want to put U1 in the first column, U2 in the second column, and then our matrix D and that gives our factorization Q equals UD U star.